Hello everyone, welcome to the last lecture of the course Metal Additive Manufacturing. I will have to summarize the course in the end of this lecture as well. So, this lecture is on Industry 4.0 and the metal additive manufacturing. I will have to introduce the concept of Industry 4.0, the 4 revolutions which the world has been through. Now, Industry 4.0 design principles, smart manufacturing, harmonizing the TRL, that is technology readiness level, and Industry 4.0 future with additive manufacturing, some example companies who are employing the concepts of the Industry 4.0. The term Industry 4.0 coined by German manufacturing industry used for the next industrial revolution. It is a convergence of industrial production and information and communication technologies. So, what is Industry 4.0? We will try to discuss it a little. Industry 4.0 is characterized by a paradigm shift from centrally controlled manufacturing to decentralized production. Decentralized means remote production or smart production or having a virtual factory using certain tools. We have the Internet of Things as one of the entities or elements, major elements. Then we have cyber physical systems which helps the Internet of Things, that is the components or the sensors to connect with the factory. Then we have the smart factories. The smart factory, it is connected by sensors, HMI instruments and robots which are monitored by a monitoring tool and a control system. What is this fourth revolution? We have been through the different revolutions which we will try to see here in the history. Industry 1.0, Industry 2.0, Industry 3.0. When the steam was developed first, when the steam was explored as one of the sources to have the mechanical advantage from it, that was Industry 1.0, when mechanization of processes using steam power was there. Then later in the time of the Edison, Tesla, electrical power was brought into use, then mass production using assembly lines was possible. Industry 3.0, this is the time that the people of my age have witnessed where the computer and automation were there. Since 1990s, the computer came as a tool which can help to compute faster. Later, the space constraint which was there earlier, only a 2 MB computer was loaded in a full truck. So now we can have multiple or thousands of GBs or TBs of data in a small pen drive size gadget. So now Industry 1.0 was from 1800 to 1913. We started in United Kingdom. Use of steam in industrial equipment was used in manufacturing. Rare or no focus on production rates or productivity was there because only the use of some mechanized system, some external power source, that is steam source, was only explored. Design and layout of these factories did not follow any scientific methodology because whatsoever was coming, nothing was laid out and it was only being used. So from 1913 onwards, when the automation of the systems was possible, then Henry Ford first developed a new system designed for producing very specific products like cars, buses, airplanes, which were put in the conveyor lines. This was some system which was based upon internal combustion engines and electrical devices that it was used to manufacture the products. Then Industry 3.0, in which the computer applications came into manufacturing and the person was able to work using CNC, computer numerical control. Before even that, the numerical control systems, the level of automation increased during this period more than the Industry 2.0. Increased efficiency and effectiveness of manufacturing enterprises and through programming, planning, controlling techniques. These came with the multiple management techniques like material requirement planning, manufacturing resource planning, then we have enterprise resource planning. Everything now is being converted into digitalization of the manufacturing. What we call generally is as product life cycle management of the industry. In the product life cycle management, there is a sustainable product cycle management as well. So this is what Industry 4.0 is now connected to. Here, higher computing and analysis power is there, which means the rapid increase in data volumes, cloud storage, computing power, network connectivity, this has all enabled analysis of the operational data that was previously almost impossible. Then we have enhanced product development. By product development, I wish to say here is that the advancement in the analytics capabilities. The product analysis required a successful and strong and solid analysis. The higher would be quality of the product analysis or product development or design, the better would be the quality of the end product as well. Now we have seamless interaction, that is we can connect through various elements, various sources, that is the human and machine interactions are now possible. These include the development of AR, that is augmented reality, mixed reality systems which make use of the touch interfaces and other hand-free operating system as well. To lay down the characteristics of Industry 4.0, number one, vertical integration of smart production systems. The essence of vertical networking stems from the use of cyber-physical production systems which lets factories and manufacturing plants react quickly and appropriately to the variables such as demand levels, stock levels, machine defects and unforeseen delays. This means the vertical integration is possible. Earlier, to pass the document from one place to another, it took time. These days we have WhatsApp, we have the internet, the computer that I showed you in the demonstration in the laboratory, that was cloud control. Being in some other city itself, I can give a command and set the printer right. So this was all taken as vertical integration only. And the flaws in the machine, everything could be seen there. Then horizontal integration is also possible through global value chain networks. That is, the relationship between the business partners and the customers or integration of new business models across the countries is also possible. Then through engineering across the entire value chain, the complete life cycle of product is traced. From production to the retirement, they must be focused on quality and customer satisfaction. So the manufacturer must build products to meet the customer's expectations. Acceleration of manufacturing production, once started, should be improved constantly so that the demand can be met, let alone the possibility of halting the manufacturing ever. So this is possible through Industry 4.0 principles because we have sensors, we have the online monitoring systems, in situ control and monitoring, everything is possible. Now to elaborate these design principles, number first is interoperability. That is, this requires an entire environment with fluid interaction, that is the flexible or the smooth interaction and flexible collaboration between all the components. Then virtualization means monitoring of actual processes and machinery that takes place in a physical world and returning sensor data. So this will then be linked to a virtual models or a models which are created in a simulated model. And decentralization means it supports the different systems within a smart factory to make decisions autonomously, that is decisions be taken by itself by the machines without deviating from the path toward the single or ultimate organization goal. The system is set in such a way that the organization or the upper level of the hierarchy set the system that the changes if small are there, the machine itself, the machine or the operator itself can take the decisions there based upon the laid criteria. This is decentralization. Then real-time capability. Real-time capability means this requires the production process to collect the data and feedback and monitor the processes in their real time, the achieved real time, that is the live data monitoring or reading is possible now. Service orientation. Service orientation, that means the Internet of Things creates potential services that others can consume. Therefore, internal and external services are both possible, and these go through the requirement of the smart factories, which is why the Internet of Things and Internet of Services should be important component of Industry 4.0. Then modularity, this is where our additive manufacturing comes into play. That is, we can propose or we can put a flexible and modular designs. So flexibility is an important principle in Industry 4.0. So smart factories can easily adapt to the changing circumstances. So that is why the system is developed in modules. Wherever requirement is there, the change could be made, the system could be or the component could be replaced, expanded, improved, worked upon with minimum disruption or disturbance to the other products or the production processes. Now, building blocks of Industry 4.0 would be big data and analytics. The manufacturing sector is finding itself busy with an increasing amount of data from various sources which even not needed, and use the analytics provided by the data sets to support management decision making. So big data means a large amount of data. Each machine would be producing data each second, maybe each millisecond. Then each machine, each element of the machine, each operator, this data keep on getting accumulated, makes a bigger data. To how to handle the data, how to envelop the data into one, there is something known as data envelopment analysis. There is something known as big data analytics, in which various tools could be used. So these different real-time monitoring using data analytics is possible through big data analytics, which is the part of the Industry 4.0, the connection which pertains to sensors and networks, the cloud computing, the cyber which involves the model and memory, the content and context of the system, community or sharing and collaboration between the stakeholders, then customization. This all is having a lot amount of data which is big amount, and that is known as the big data. Now, autonomous robots. The robots in the Industry 4.0 scenario are, if not fully, but partially or largely autonomous. That is, they take the decision by themselves, whether the piece is defective, they do not use it. If the piece is usable, to try to only select only that. So based upon the techniques, the different techniques, the contact and non-contact techniques that we have discussed in the non-destructive testing, that we have discussed in reverse engineering system as well, the robots can visualize, they can touch, they can have certain small control system and try to be autonomous. We're designing robots to be self-sufficient, autonomous and interactive, so that they are no longer simply tools used by humans, but they are already integral work units that function alongside humans. So these days even there is a concept of cobot, a robot working in collaboration with human. Whatever, so for example, there is a large force required to do something with hand, I develop a cobot, whatever force or whatever movement I do, the cobot will do the similar. So similar, for example, for a dental surgeries or so, people have now started using cobots. The cobots will try to only work as per the direction, as per the movements given by the dentist itself. So there is these concepts. So these are the also concepts which are now the part of the recent technologies. Simulation. Simulation means imitation of reality. The previously manufacturers wanted to test a process, it working efficiently and effectively, trial and error was required. Industry 4.0 uses virtualization to create digital twins. Digital twins means there is a physical system, we can create a digital systems very similar to that. For example, if there is a motor, if I try to run this motor in an overloaded condition for the extended number of hours, at what point the motor gets heated. I create a digital system as well, that after 5 hours of the overloaded condition, the motor will start heating or so. This digital model would also show the heated part of the motor. So digital and the physical system there is. So these makes the digital twins. This is virtualization of the system. So these are used for simulation modeling and testing, and they will play more major roles in the optimization of the production. So there is something also that I just mentioned, product lifecycle management, PLM. In this also, first is the design, that is the CAD models, then we have digital plants. That is also a second portion of it. Then we have the digital enterprise resource planning. So this is product lifecycle management contents in general. So digital plants, here we can see a digital plant in a way, the machines could be kept here at vertical places, how the material flows from one machine to another, how the robots will pick the machines. This all is possible, and simulation is now not only limited to the static or the dynamic simulation that we do for the product or for the component. We can even move to the system development, that is the manufacturing or factory development. Now horizontal and vertical integration, which I just discussed here, the goal is to create scenario where engineering, production, marketing and after sales are closely linked. Similarly, companies in the supply chain will also be more integrated, giving rise to data integration networks, collaboration at automation level, and value chains that are fully automated. Industries 4.0 is there, so in which we have the horizontal integration, also we have the vertical integration, we have Internet of Things and IIoT, that is Industrial Internet of Things. So that helps us to make the operations can have horizontal and the vertical interaction as well. The industrial IIoT, the embedded computing and networking will connect sensors and devices which are an essential part of Industry 4.0, Industrial Internet of Things and Consumer Internet of Things together help us to bring the 4.0 reach maximum. We can have smart cities, we can have the consumers having their wearables, phones, TVs at homes where they can monitor and see the systems, and they can monitor their health, they can monitor their businesses, they can monitor their homely activities. All these things could be used. Cyber security, the industrial systems are becoming increasingly vulnerable to threats, as can be seen by recent attacks on industrial targets. So to install these systems is not only for automation, just to keep oneself safe also, some has to understand the system. For example, if I am using a computer, I need to understand what are the virus threats to my Windows or to my other programs which I am using. So for that itself, the cyber security systems are to be understood. The cloud, the data sets which are involved in Industry 4.0 means data sharing will not only desirable but imperative. This is imperative to leverage the full possibilities within the value chain. So this data can be stored in cloud. We can only have access to the cloud and try to collect the data or use the data when and wherever necessary. Augmented reality is close to what I just discussed about the digital twins. So virtual reality, you all understand, is something, a factory or a machine in a virtual environment where completely virtual environment is there. Augmented would be the virtual environment augmented with the human interaction. Mixed reality is also there where some part is virtual and some part is completely human. So augmented reality, where businesses are increasingly looking to reduce the maintenance and training overheads associated with production, marketing and after sales support. Next comes our core thing, additive manufacturing. Additive manufacturing such as 3D printing enables manufacturers to come up with prototypes and proof of concept designs which greatly reduces design time and effort. This is what we are trying to focus in this lecture. And how is this possible? Let me try to see what is a smart manufacturing. In a smart manufacturing, it is a process of improvement initiative in production. It aims to merge the digital and analog worlds by building connectivity and coordination to provide enhanced processes that deliver goods smoothly and consistently. So what systems are required in a smart factory? The first issue with smart factory or smart manufacturing is connected about machinery and equipment. A cyber physical system and advanced sensors work together and connect to systems that can control and orchestrate the production process by sensing the condition of the product being manufactured. So this is how a smart factory in general works. In a cyber physical system, we have satellite networks, we have the Internet of Things in which RFID is one of the tools, we can have QR and some other systems as well, the internet, the embedded systems, the wireless sensors. These are all the cyber physical systems which are the part or the equipment in the smart manufacturing system. So we redefine the workforce. Workforce doesn't only mean that we need to have separate engineers, technicians, managers or HR planners. They are to be connected. Each one should be able to understand the other person's work, because smartly working on a single platform, if suppose we are using a project management software itself or project management tool itself like Trello, like Jira, like maybe Google Suite or so, there also where to put data, who is going to access the data. In this case, we also need to redefine what workforce or what kind of training our employees need to have. People are as equally important to smart manufacturing as machinery. Therefore, technicians, inspectors and process operators must be connected via function-specific applications. Managers also need connectivity to the manufacturing process while dynamic real-time dashboards that display status, trends and alerts. The workforce of the future will most likely require multidisciplinary generalists with computer, mechanical, and process engineering skills. The products in smart manufacturing, one of the goals for smart manufacturing system is that the parts and components should be identifiable and smart. For example, they should be able to identify themselves and hold important information. For this case, sometimes the components which are there, again we can connect the components of the boxes which are the cartons which are assembled or which are shown in this assembly line. We can mark a small QR here, or we can also put a RFID code here, or we can see whether what is the distance between these components. The colors could be marked different. So all these things, the products should be able to identify themselves. This is how we try to automate the system. Either we try to put the sensors here in the robotic arm, or we try to put it there with the augmented reality systems with humans, some sensors or some gadgets they might carry in the hands, or they might tie something on the wrist, a band or so, or we can also put something on the components of the systems itself, on the boxes. So a manufacturing plant, a global facility inside is something like this. What makes Industry 4.0 a practical or realizable or implementable system? Network systems provide connectivity for localized decentralization information processing. Progressive miniaturization allows for small auto ID for customized product manufacturing, creates unique identification and links to the virtual world. Intelligent field devices using software that allows for the global dynamic distribution of functionality. This is an integral part of the system integration. Mobile device management also makes the man-machine interfaces for the intuitive operation of complex systems without special training. Now, there are major challenges that the time and the cost for further increasing and the overall readiness level of the fusion energy, that is system developing the system here, which we say the different systems are there: cyber physical system, Internet of Things, additive manufacturing, human, machine, robots, all those are to be fused together. That is why we need the overall readiness level, that at what point are we now. Testing materials under extreme environment, data collection, analysis and assessment, new design of components. So Industry 4.0 is on its way as of now. Trend to use automation and data exchange technologies, that is cyber physical systems, Internet of Things, cloud computing, cognitive computing to perform industry activities. Nuclear sector has not yet caught up with Industry 4.0. This is an important mention. So we started from mechanization Industry 1.0 to electrification Industry 2.0 to computerization, the third revolution, now digitalization as the fourth revolution. Next, I think I would like to also discuss the TRL, the technology readiness level, and we will try to see how additive manufacturing has helped to lower the TRL level requirement in order to take the product to the really marketable or sellable position. So this is TRL, that is technology. By technology we means the process, the method, the machinery, the equipment, the techniques or the software, anything that could be technology. And its readiness. Readiness means how mature the technology is. Is the technology really capable of doing something in real world, or are we only in a redesign phase or so, that we will see in this table. And the level. Technology readiness level. Level would be actually the real maturity, that is being used or being developed. That level could be set in these 9-point scale. So point 1 to 4 is the basic principles of the technology. Point 1 is the basic principles, in which we can see this is a technology readiness level template for the practical use, how do or where do the technology lies. So it could be the whole system, what is the level from the material viewpoint, from the methods being in the technology, from the manufacturing and in the instrumentation. So first level is the basic principle. Basic principle means the fundamental attributes that have been established, in which the evidence from the literature is taken. The evidence from literature is taken in the methods, process concepts and proposed in manufacturing. Understanding the physics is there in instrumentation. So this is the basic principle. Next comes the technology concept. What is invention and what is research, or what practical application could be created later, as well as the phenomena to be investigated, the knowledge that is to be learned, knowledge to be integrated. In this we try to see whether agreed property, targets, cost and time scales are there in materials. In method we say requirement, definition produced, then validity of concepts and describe, concepts designed in instrumentation. Then in the third level we have the proof of concept. Proof of concept means at least a theoretical illustration of how the invention might function. We have at least a small design, maybe not design, the draft ready. So in this case we only call it, this is only research, I would put it here. This is only the research about the technology. Then comes the validation in a laboratory environment when we have the first prototype ready. So this is the technology development level 4, which we call it is a bench scale level. That is, the product starts taking the shape in the laboratory or in the research facility. So we have, in the case of material, design curves produced, we have small monographs maybe. So methods would be validation of a standalone environment, a specific environment. For example, it is not a scenario analysis, it is only the sensitivity analysis, keeping everything else constant. My product would behave or would have this much of the deformation when I try to see the tensile strength. So something like that, everything else is kept constant. That is a standalone environment. Then manufacturing processes validated in the lab, laboratory demonstration of highest risk components, that is what is the highest risk. So those things are taken here. This is the level 4. Then we have the level 5, in which partial system validation in a relevant environment is there, which means the pilot scale or the product which is now is from maybe a medium to little high fidelity level. The fidelity level changes. At the level 4, it was only the low level, I would say low fidelity level only. So in these methods for material processing, component manufacture, in the material, in the methods we have partial validation of basic functionalities. In the manufacturing, the basic capabilities are demonstrating using production equipment, and requiring specialist support is there in the instrumentation. Then we come to the level 6, which is the large scale, that is the prototype in a relevant environment. So this becomes the next level. So till level 6, where the large scale component is now available, that is the testing at the close or full scale dimension is now possible. The equipment will still be in the process of modification because certain designs or feedback might come from the customer who are using it, the first customer we are trying to use. When I say customer, it doesn't mean the final customer, it is only the internal customer or the laboratory people who are trying to test or who are trying to see the level of the prototype that we have developed. So they agree on the integrated product and is verified. The process is optimized for capability in manufacturing. In instrumentation, this is applied to realistic location environment with low level of specialist support. So in this case, till the point 6, we can say development has happened. Right? Now comes the level 7. Generally, when patents are filed, those starts from design patent is only registered at level 3. From the prototype level, generally the patents start from level 4. If it is level 5, that is the prototype now demo could be given in a professional environment. Why I am trying to talk about all this is, I will try to connect this to the additive manufacturing, that while having additive manufacturing systems possible now, the TRL level from where we can take the product to the market is now brought to the lower level. Now in the 7th level of the TRL, the technology is now ready to be passively commissioned. That is using inactives similar to those anticipated during the operations. The work testing or the field trials could be taken. So full throughput is now anticipated here. It is validated through the production usage, the methods, the economic run lengths at production plants is taken for the manufacturing. In instrumentation, successful demonstration in the test is taken. So here I have started my deployment. So this deployment continues till level 8, where the test and demonstration is now taken at a active commissioning level. That is, actively the technology is being commissioned, it is fully operational test, it is the release into the production library, the methods, significant long runs for the full time production it is now taken, and the instrumentation is demonstrated, productionized system. So this is deployment. Finally, we get the operations or the final use, actual use, I would put it as operation at the technology level or TRL9. At TRL9, successful mission operation is there. That is, operations are now ready, the technology is currently being used in an operationally facility, the product is finally being used by the customers. So successful mission is there, the material production, ready materials we have, full production system we have in the methods, in manufacturing we have demonstrated an extended period and service is proven. Now the point is that, in general, some levels of the technologies are there. For instance, if I have a technology in which I need to put the TRL level, generally I will say it is from the system viewpoint, I am only at the partial system validation, that is I have come to my development, the prototype is ready, but still it is not completely validated. However, the materials for the prototype are validated to some extent, that is I have evaluated and tested the material part of that, and development rig tests have been taken. Similarly, the methods have been tested. So I'm just putting some hypothesized system or hypothesized technology which I have, in which the TRL level for at different functions would be something like this. For the methods are validated through production usage, and even the materials and methods, if those are validated, but manufacturing level could even be lower. That means I do not have the economic runs yet, but the process is optimized for the capability rate using the production equipment to some level, and the instrumentation is still also not ready because the production system is yet not tested. So instrumentation only requires still a little specialist knowledge. That instrumentation would only finally come when the technology would be ready, and I'm very sure that the methods, the materials, the manufacturing system is there, then only I will understand what instruments are required finally there in the technology. For example, this is the status of the technology. TRL level is this 5, starting from 5, because the prototype is now ready. In the absence of additive manufacturing, what used to be, we used to develop the prototypes using the conventional manufacturing systems only, and we were not able to have the feel of the product. Now, let me have 2-3 cases here. Case 1, the old system, let me say, have a technology that starts from level 7, and the time and the cost which is being invested is something like this. So first case could be the technology could start from a level lower, because at level 7 I have completely tested the product. Using additive manufacturing, I have developed the product in a lesser amount of time, or in the beginning at a level 5 itself, when I had the first prototype ready, I was able to develop some components of them. So only 1 step lower than this or 2 steps lower than this, I am able to do that, but the time taken is little higher. Another case could be when the old system at 7, it is still stuck and continuously, and still with the long running times, I am not able to get any improvement, but still here using additive manufacturing, you can have the system here, but we are not able to get up, then this time is still kept here. So another case 3, which is now the enhancement of case 2 using additive manufacturing or using something that helps us to understand the methods, the manufacturing better, we can able to rise little higher level, and we can reach the target here. The product reaches the customer. Finally, this is the case in which innovation and industry 4.0, if everything including the additive manufacturing, those come here, these points are actually known as the target gates. So this is something that I showed you in the previous slide as well. This is my target gate. That is at what target gate are we, or from where are we trying to reach to the which level. So in this case, I could say here that technologies with lower TRL are not tested or not taken further, because you can see in the case 2. So the time and cost is being invested continuously, but still the technologies are not able to mature or not able to go to the next level. So that is why the technologies don't go here. We do not use, or I would say in the case 2, that additive manufacturing is not used. Now, the technologies with low TRL, are no more much risky. I would say TRL low, not risky with additive manufacturing, or maybe also with the help of Industry 4.2 Internet of Things or so. So this is what is the benefit of additive manufacturing or the role of additive manufacturing in the overall scenario of the Industry 4.0. So it is also mentioned here, technology with low TRL today need not to be a risky choice, and development plan will help to reduce the risk, because we will have the product in the physical form in our hand, we can have the feel of the product. Maybe suppose if the final product is made up of in colon or so, at least with PLA, the first feel or the size of the maybe scaled down model of that we might have in our hand, and we can call it a low fidelity product, and we can see the actual shapes, holes, movement of the different materials within that component. Now what I am trying to say here is that we are able to integrate the safety within the design. That means this was the previous system in which requirements were there, from the requirement design was made, that develops us to help the safety graph and everything, then we have the regulatory improvements. This was a waterfall, that the way it keeps on coming, it keeps on letting the things come to the ground, and it keeps on giving us the final result here. Nowadays it is not the waterfall, it is now a spiral. By spiral I means the design, requirement, regulatory improvements keep on going hand in hand, because we are able to see the design or change the design or change the product or present the product, and the level of the design, level of the requirement is keep on increasing as and when, and keep on moving along this spiral. That is, safety layout is also now quite high. This is how the system is keep on going with a very low level or lower understanding. Here the understanding level, when I move from the region in any of the directions, the understanding level is increasing. I would say better understanding the product. Or I would say TRL is higher. Now Industry 4.0, the future in developing countries like India, we can see how important industrialization is to economies as income rises when productivity grows. Services such as logistics, advertising, marketing make up an increasing amount of manufacturing time and expense. Industry 4.0 places high importance on the Internet of Services, where manufacturers can create or consume available services within their value chain. These services such as inventory control, logistics, and smart transportation will reduce costs, improve efficiency, and ultimately the productivity. So how are we working now, and what are we trying to reach to? Industry 1.0, 2.0, 3.0, 4.0, also Industry 5.0, we are co-working. That is, the cyber physical systems which I just talked about, the human and the robots might work together, the cobot systems that might be called as Industry 5.0. That is, the safety has to be risen, we need to be more safe while collaborating, while working with the robots. However, the costs have to come low. This is the target, or this is what is being approached in the Industry 5.0 scenario. So future additive manufacturing, if I try to mention here is, so we have Industry 4.0, digital process chains, system technology automation, scalable robust additive manufacturing processes and materials all in one. These all systems are integrated here, 1, 2, 3, 4. And that is the future additive manufacturing, that is the collaboration of the systems, which helps us to have a comprehensive cooperation platform for highly integrated cooperation and use of the decentralized distributed resources. So this is how it is possible. Industry 4.0, digital process chains, the materials, the system technology and automation, all these would help to have a future additive manufacturing system. So this is also known as a virtual laboratory system. So if I call the additive manufacturing components in 3D printing, the selective laser melting, suppose as a metallic component, the quality of the build depends upon the parameters that can be over 100 parameters. Dimensionality reduction done to optimize and reduce time and cost of manufacture. This can be taken further into a virtual laboratory where you redesign initial component, additive manufacturing production with the selective laser melting, advanced materials, multi-materials, automated post-processing with support material. Everything becomes automated, and this could be applied in medical technology, automotive systems, turbo machinery, aerospace. So this is how additive manufacturing is connected to Industry 4.0 very closely. With this, there are certain examples like General Electric. They call it a brilliant factory that uses industrial Internet of Things technology in some of its manufacturing plants and aims to introduce smart technology ultimately within the company's 400 manufacturing service plants. So they say that 50 B machines becomes connected using the industrial Internet of Things, not within the plant, not within the room, but across the factories that they have using industrial Internet of Things. Similarly, Airbus have a connected tool in manufacturing. It is working with National Instruments to create what they describe as a factory of the future. The first phase of the smart system targets the reduction in mistakes and waste of time and material and lean manufacturing concepts. So Airbus is also employing the system where riveting, tightening, everything is monitored using the system, whether the rivet, the torque is given, whatever force is given for riveting, whatever torque is given for tightening, everything is being recorded in this system. So these are practical examples. Similarly, Siemens Embedge electronic plant is a faster production line and can mount 250,000 components per hour. They also use the systems such as the big data, the factory internal connections, using the systems, using the cyber and the physical systems, using the Internet of Things, using the concepts of the Industry 4.0 in manufacturing. Now, to want to ponder in this lecture is list the elements of Industry 4.0, what are Industry 4.0 design principles, explain the term smart manufacturing, how are TRL levels contracted using Industry 4.0. With these points, if you try to answer, you will be able to understand the contents of this lecture. With this, I try to rest the course on metal additive manufacturing, where we discussed multiple things. I will just have a quick look or summarize what we have discussed through the various weeks. In the week 1, we gave a brief introduction to the metal additive manufacturing. What is metal additive manufacturing? What does this course had? And we compared the metal additive manufacturing with the subtractive and need of the additive manufacturing that was given. Classification of metal additive manufacturing and challenges associated with it was discussed in the second lecture, in which a long-term game changer how additive manufacturing could be, then current and the future estimation of the size of the market, then challenges and opportunities were given, applications of additive manufacturing was taken as a third lecture, then various terms associated with additive manufacturing, that is the glossary was given also in the week 1. Week 2 majorly discussed about that design, that is the computer aided design in metal additive manufacturing, the modeling and data processing. Then we had issues with the STL file format, the slicing, design consideration, machine setup. Then we had the basic processes, starting from the very basic processes such as the powder bed fusion methods, the directed energy deposition methods, binder jetting, then some emerging processes such as material extrusion, material jetting, sheet metal lamination, these were discussed. Week 3 then started talking about the laser and the electron beam processes. In the laser processes, the system setup for the laser machines, the laser theory in general, the components of the laser machine, the difference between continuous and pulsed laser, laser types, laser beam properties were taken. Then we had discussion on the electron beam processes, where the difference between the electron beam and the laser beam, then electron beam powder bed fusion methods, electron beam mechanisms were taken. Week 4 discussed about the powder and wire fed systems, in which the development or the production of powders, the bed delivery and spreading systems, the wire fed systems, everything was discussed. Important physics was discussed in the lecture on solidification of parts, where the cooling curves, the iron carbon diagram and various metal interface diagrams were discussed For example, we had a discussion on the nickel and aluminum interfaces, then theory of mechanism of solidification in equilibrium phase, in non-equilibrium phase, these things were taken. In week 5, the process parameters in general, though the process parameters would be different for different kinds of the systems, but in general for additive manufacturing, the certain process parameters, and there were also discussion on the powder properties for the powder bed fusion, for DED, for binder jetting, all the methods. Then ambient parameters for the powder bed fusion and DED methods were taken. Mechanical properties were also discussed in one of the lectures, in which the properties such as the hardness, the tensile and static strength, the fatigue behavior were taken. The common defects in additive manufacturing and the post-processing methods in additive manufacturing were taken in the next lecture. Week 6 discussed about design for metal additive manufacturing. In that design, it was discussed DFAM, design for additive manufacturing. Then also we discussed about the modularity, the application field of the design for additive manufacturing, the slicing systems, the design assessment, design making, opportunistic and restrictive designs were taken. Topology optimization theory was also introduced in the next lecture, in which how do we reduce the weight, reduce the size of the component, and how do the CAD softwares helps us in that. So this was discussed. Then in the week 7, on-machine sensing and in situ control system were discussed with the basic principles for the on-machine sensing, factors affecting these systems, spatially integrated and spatially resolved sensors were taken. Then we had in the week 8 the additive manufacturing of the metal matrix composites, because hybrid manufacturing is also there in the additive manufacturing system, in which the ferrous matrix, the titanium matrix, aluminum or nickel matrices, all those things are there. So these were discussed. In the week 9, reverse engineering was taken. In the reverse engineering, what is the methodology, what are the different steps in reverse engineering, what is the need, how do we justify this. Then a laboratory demonstration of this was taken using the Comet 3D 5M scanner. Then CAD and topology optimization laboratory session was also taken, and a lecture on non-destructive testing, in which the contact and non-contact type of the non-destructive testing systems. In the contact type, ultrasonic, eddy current, magnetic, penetrant, acoustic systems were taken. In the non-contact, radiography, thermographic, visual inspection, X-ray systems, these were taken. Then we had in the 11th week the sustainability in additive manufacturing. In the sustainability, how do we develop the green additive manufacturing or the sustainable additive manufacturing systems, specifically in lean and green business model, and design guidelines and design rules for sustainability. These were taken. Metal 3D printing laboratory demonstration was then given in the week 11. In week 12, we had a small discussion on the safety, which is very important concern, the kinds of the safety, the inductive and the deductive type of safety systems. Then we have discussion on different models in costing additive manufacturing, in metal additive manufacturing, where pre-processing, processing and post-processing costs were taken. In recent lecture, we have industry 4.0 and metal additive manufacturing, and how metal additive manufacturing plays a big role in the industry 4.0 application or implementation, and what future in metal additive manufacturing and industry 4.0 is there. With this, I would like to thank you, all of you, for sparing your time, for being in this course. Knowledge is a continuous process, and we'll keep on learning, we'll keep on adding more and more to our plate, and this will continue in the future as well. Thank you so much.